what we've studied so far is area under one curve. So if I had my x and y axes and I had a parabola, I could figure out the area under that curve between 2 points. So let's say I chose this point and this point. I could find that area, and of course, we got really good at coloring. Did anybody go back and watch the coloring? Yes? Was it relaxing? Was it made you laugh? Good. So we could, on YouTube, does it come up as the coloring thing? As a picture? Oh, that's disappointing. So we could find the area under that curve from there to there. And if I had another parabola, we could also find the area of that curve from the same red points underneath that curve. If, oh, this will be strategic, if I color that area in crayon, that's not crayon, in crayon in white, that would be this area. Oh, I like this. This is also the first time in my teaching career that I have strategically used the white crayon. It's really also somewhat enjoyable and somewhat frustrating that you can't quite get it all. There we go. There. There's a few pixels that are still purple, but I hope you get the picture that if I can find the area under one curve, and I can find the area under another curve, and I specifically chose those points where those two curves met, I can find the area between two curves. I could now say that what's left of the purple, I could figure out by just doing what I did. Figure out my purple and subtract the other one. Figure the area from the curve above and subtract the area from the curve below, and I'll be left with the area in between. And now we get to find some really odd-shaped areas. Because up till now, we had areas where the sides were straight lines, the bottom was a straight line, and the top was curvy. And we were like, ooh, exciting. But now, the top can be curvy, the bottom can be curvy, because we're finding the area between those two curves and just using the idea. So if we take the area of one, subtract the area of the other, and we use our properties, we can actually put that together as a single integral and simplify our equations even before we start. And the really nice thing about getting the area between two curves is that process of subtracting one from the other does not matter where our axes are. So for example, I'm moving my axes up here. Can you see that in our problems before, we would have said, ooh, this is a little bit messy because some of the area is above the curve and some's below, so some is positive and some is negative. And then we had to figure out different parts when we were trying to figure out the area between the curve and the x-axis. The nice thing about area between two curves is that it doesn't matter where your axis is. The process of subtracting one from the other eliminates the problems of the axes and the negatives, and you will get the correct area between the curves no matter where your axes are. So in some ways, this might be even easier than before. So here's our first example. Find the area between the two curves. If you have a basic knowledge of graphs, you'll be able to tell which is the graph on top and which is the graph on the bottom. So if I was going to draw these off to the side as a picture, and my picture is not necessarily going to be that accurate, but can you see that one parabola is opening down? And another parabola is opening up. The parabola with the y-intercept of 10, so my graph is somewhat accurate, looks like that. My parabola with a y-intercept of 2 opens up. And I get an idea of what's happening. I want to find the area between those two curves. Okay, so I'm looking for this area. You notice that lightning purple every once in a while? Like, okay. Shocking. So we want to find that area between the two. And we can do that by finding the integral. But in order to figure that out, we need to go from this point until this point. This will be from point A to point B. And I need to know what those values are. So that's going to be our first step. First, we need to find where they intersect. How do we do that? How do we find where the blue graph and the green graph cross each other? We can solve the equation, right? We can make them equal to each other. They're both solved for y. That would give me, from the green graph, that x squared plus 2x plus 2, the green graph needs to equal the blue graph of negative x squared plus 2x plus 10. So if I bring everything over to one side, I will get 2x squared. The 2x's cancel out. 2x squared equals 8. X squared equals 4. And x is equal to plus or minus 2. Okay, my graph wasn't very good, but wait for it, wait for it. Move the axes over. There. We'll just say that, and this little 2 is still there, and this little 10 is right there. Perfect. A little bit more accurate graph now. So now we found that it intersects at -2 and +2. So we can now find the integral, the area under one curve, minus the area under the other curve. So again, I'll color code it. Our area in purple is going to equal the area under the blue curve from -2 to 2 of the blue curve, which was negative x squared plus 2x plus 10 dx. And then we're going to have to subtract from -2 to 2 the area under the green curve, which would be x squared plus 2x plus 2 dx. Now, neither of those integrals are exceptionally difficult to figure out, to integrate. However, if you know your properties of integration, and you know that if you're going from the same values of two functions that you could put those together, it makes sense to do so. Because then my area becomes the integral between -2 and 2. And if I subtract them, I end up getting some like terms. Negative x squared minus x squared would give me negative 2x squared. 2x minus 2x would go away, and 10 minus 2 plus 8 dx. And that integral is actually simpler to calculate, and we have much less calculations to do as a result. So my area is equal to negative 2x cubed divided by 3 plus 8x from negative 2 to 2. Plug in the top value, negative 2, and we would get x cubed divided by 3 plus 16. Plug in negative 2, you will get positive 16 over 3 minus 16. (16 plus 16 would be 32. Negative 16 over 3 minus 16 over 3 is minus 32 over 3. Which in the end is equal to 64 over 3. Nice. So the ideas that we're using here is nothing new, all skills that you've learned before. You found out how to find the intersection between two graphs by solving that system of equations. You found out how to do the area underneath one curve, and now you have to take the area underneath one curve and subtract the area underneath another curve to put them together. Knowing our properties of integrals allows us to combine that together, so our integration is even simpler. And as a result, what we figured out, I know I've taught this many times, I still find it amazing that we figured out that area between two parabolas relatively easy and without a formula. Right? There's no formula. I no longer get excited when I figure out the area of a rectangle with a formula. It's just not invigorating. But this hasn't worn off. When you think about what we just figured out, it's quite amazing. All right, one for you to try. It's nice to start off by drawing a picture. So if you have a parabola opening up and another line, this would be the idea of the area between them. Now, if you ever screw up and do the wrong one minus the wrong one, you will get the right answer, but it will be negative. And so instead of erasing all your work and redoing it, you could just go back and put absolute value bars around everything to say, I meant to do that right from the beginning. But in this case, if you can draw them, you could see that, hey, I should put the line on top and subtract the parabola, because that's how the area between them would make sense. So first of all, we can ignore these absolute value bars, because you wouldn't need them if you did it in the right order. Again, if you can simplify first, it makes your life easier. So after simplifying this equation, you can find your integral and then plug in the values to evaluate. Get this on one whole page so you can see everything. 125 over 6? Nope. Yes? Or you got to the part where you had to do the mental math with the fractions and you just said, I'm going to wait? Maybe. So again, drawing the picture, you would know that the line was on top. Get 32 over 3. I'd be more impressed this time if you had no work showing just 32 over 3. It's like you look at the question, oh, it's obvious. Let's do this one together. Now we have a cubic and a parabola. And if we think about this, if we go to sketch a graph, it could be that they intersect in more than one place. In fact, we're going to find out here that they do intersect at more than the 2 places for the area between. So if we go to sketch our graphs, and I'll do the cubic in blue. If I was thinking about that cubic graph, I could have factored out an x, leaving me with x squared plus 2. X squared plus, I could have factored out an x squared. That's even better, leaving me with x plus 2. That means on my cubic graph, I'm going to have an x-intercept at 2 and 1 at 0. And since it's a positive x cubed, you know that your graph would go, well, what happens there? I have a problem. Well, I know what happens there, but I'm drawing the problem on purpose. Yes, okay. That part I should have seen already, but here we go. Let's erase that 2. There we go. Let's draw it at -2. That one should go away. There we go. Have you ever played mini golf on the smartboard? Yes, some of you have. Well, we might be able to set up a mini golf game later. But right now, we've got -2, which is correct, and 0. We know that it starts from here, but at 0, because that has a multiplicity of 2, your graph is going to bounce off that x-intercept. And our green equation, g of x, I can factor out an x as well. And so we get -2 and 0 as x-intercepts for that as well. And it's possible that we have another intersection point there. So if we're wanting to find the area between these 2 curves, we're going to need to figure out 2 different areas. There's this area between the curves, which I'll do in orange. And then there's this area between the curves, which I'll do in brown. think those colors complement each other nicely. What do we need to do then? We need to find out, we know where they intersect, that they intersect at -2 and 0, obviously just from solving it, but they intersect at a third point. So if we were trying to find out what that third point would be, we could set our equations equal to each other. So our blue equation, which was x cubed plus 2x squared, and our green equation, x squared plus 2x. This is a cubic equation. How do we solve a cubic equation? Well, we make one side equal to 0. And we factor. Luckily, this one factors nicely. And even if it didn't factor nicely, we would have had some hints because of our graphs. But look, I can take out an x to begin with, leaving me with x squared plus x minus 2. And although this is relatively easy to factor, how did I know that one of them had to be x plus 2? Because from our graph, they intersected at -2. And once I have that as x plus 2, the only thing that would work here would be x minus 1. And so the intersection points happen at 0, -2, and at 1. We can go back to our graph and add some more information. If we go directly up from 1, we get to that point at 1 comma, and we could plug it into either equation, and you'll find out that it happens at 1 comma 3. So to find the complete area enclosed by these two curves, we need to find the orange area and the brown area. The orange area goes from -2 to 0. The brown area from 0 to 1. So if we go down and say our complete area will equal. Now the orange area, which I'm going to represent by taking out the crayon and making the integral sign with an orange crayon, went from -2 to 0. And in the orange area, notice that it was the x cubed graph on top and the parabola underneath. So we're going to need to do our cubic function, which was x cubed minus 2x squared, subtract our parabola, which was x squared. Was it plus 2x squared? Thank you. Plus 2x dx. Move things over. There we go. And then we have to add our integral that was colored in brown, so I'll represent that with the brown integral sign. That went from 0 to 1, and now the parabola was on top, and the cubic function was underneath. So now it would be x squared plus 2x minus and since the brown integral goes from 0 to 1 and the orange integral goes from -2 to 0, we cannot combine these together to be a single integral. The property says that only happens if they're going from the same value to the same value. And since they're different functions in between, we can't just do the integral from -2 all the way up to 1, because they do a flip-flop of which function's on top and which function's below. If you did go all the way from -2 to 1 with one of them, you actually would have one area subtracting another area, and your answer wouldn't be complete. So it's a little annoying that we have to do each of these separate. Okay? Again, it makes sense to simplify first. So in the orange one from -2 to 0, I would be left with x cubed plus x squared minus 2x dx. And in the brown integral, from 0 to 1, I'm left with a negative x cubed minus an x squared plus 2x. So I feel at this point it's just a lot of fairly easy calculations. I mean, not just tedious. We have to plug in our values, one minus the other, plus why did I make my brackets that way? Okay, first I have to plug in 0. Whew. Feels good. But then I have to plug in -2, so this will be 16 over 4 minus 8 over 3 minus 4. Then I plug in 1, -1 over 4 minus 1 over 3 plus 1 minus 0. 16 over 4 is 4. 4 minus 4 is 0. This will be -8/3 times a negative. Positive 8/3. Get a common denominator here. -3 over 12, -4 over 12, plus 12 over 12. Plus 5 over 12. Get a common denominator here. 64 over 20. Oh, I get 12. Don't have to go that high. 32 over 12 plus 5 over 12. 37 over 12. What we're going to do now is we're going to see if we can use our graphing calculator to help us with this even better. Yes? Yes. Now, I'm going to draw this out. X cubed plus 2x squared in y1, and I'm going to graph x squared plus 2x in graph 2. And see if it shows up similar to what we had graphed. Nice. Now I'm going to zoom in on this little section, so I'm going to go from -1 up till, did I type in something wrong? X squared plus 2x. In my equations I typed in right. X squared plus 2. Oh, I forgot a 2. My goodness. Something didn't quite feel right. That looks more like what we graphed. Now I'm going to change my window. We don't need to go this far back, so maybe I'll go from -4 to +4 and from -1 up till 5. Now, as far as I know, there isn't a nice thing on your calculator, or if there is, I'm not sure where it is, that would shade it nicely between the two curves that I've gone there. Okay? So I'm going to show you a few other things that we can do. If I wanted to find the area of the orange part, which is from here to here, that would be the blue graph minus the red graph between -2 and 0. Correct? On your calculator, some things that you can do. If I want to go blue graph minus the red graph, I just need to type in y1 minus y2. There's a couple of ways that you can do that. It's under your alpha menus. You know, when you go like this for fraction, if you would go all the way over to y vars, you could go y1 minus y2. And if I graph that, now I'm going to have 3 graphs showing at the same time. If I only want to see that part of the graph, I can go to my equal signs and push enter. That turns the other graphs off. So now when I graph it, I only get the subtraction of the 2. If I go second, calculate the area under them from -2 to 0. I get the first part, which ended up being 8/3, 2.667. Okay? If I go answer, it has that value stored for me. And I'm going to just store that as the letter A for now to remember it. So I use the store button, helps it remember a value. Okay? Now, 2 things I can do here. If I think about this graph, the next area I want to find would be this one, but it's below right now. It'll end up being negative. I could go into here and in y4 type in y2 minus y1 and just turn that purple one on. The purple one will be exact flip of the other graph. But I now want to find that area between 0 and 1, 0.4167. That would be the 5/12. Again, I can go out of here and get that answer, 5/12. And I could see if the answer that I had in A, that I stored as A plus this answer I just got, if that is indeed equal to what we got as an answer. Did we get 3.08? If I change that back to a fraction, 37 over 12, it's what we got as well. So at this point, probably actually doing it by hand might be easier than doing it by calculator. Do you think? Just you haven't used the calculator that much. There's a lot of buttons that you have to end up pushing. And what we figured out wasn't too bad in the end. Just a lot of data to hold to figure it out. We had to figure out two different areas. We had to do one part where we did the cubic minus the parabola, and the other part where we did the parabola minus the cubic. Putting that all together gave us both of those areas. All right, so we are going to try some up at the whiteboard. I'll put them on the smartboard for you.